welcome to lecture 3 of the module on numerical differentiation and integration. What we have done in the previous module is motivate the idea of numerical integration and used a geometric interpretation of what numerical integration means. Specifically we considered two methods, one was the Euler's method and the second one was trapezoidal method. In trapezoidal method what we did was we tried to approximate the area under the curve as approximately equal to area under a trapezoid. So what the geometric interpretation of the trapezoidal method is if we plot f of x against x and if we get say some kind of an arbitrary curve of this sort and we want to integrate it from let us say x1 to x2, what we do is we just connect these 2 points by a straight line, and now area under the trapezoid that is formed over here is the area under the curve. Okay. So that is what we studied in the previous lecture. This is really the geometric interpretation of trapezoidal rule. Based on this particular geometric interpretation, we said that the integral I using the trapezoidal rule was equal to half multiplied by x2 minus x1. We called this x2 minus x1 as h. So h by 2 multiplied by f of x2 plus f of x1, or I will just write that as y2 plus y1, and this is the area under the trapezoid. It is half multiplied by the base multiplied by sum of the two heights. That was the geometric interpretation of the trapezoidal rule. So what we are going to do today is try to formalize a couple more ways of deriving the trapezoidal rule, and the first one is again directly motivated by this geometric interpretation. So what we are doing is we are joining a line that passes through 2 points. The 2 points are x1 y1 and x2 y2. Okay. What I am assuming over here is y equals f of x. So rather than writing every time f in brackets x, f in bracket x and some things like that, I will just write it as y. Okay. And we are interested in finding integral of y dx from x1 to x2, or in general from a to b. Okay, that is the problem that we are trying to solve. So our integral I is going to be equal to integral from x1 to x2 of y dx. Okay, so this is the exact integral that we intend to find. The approximate integral based on the trapezoidal rule is really the area under the trapezoid. So we will write that as approximately equal to x1 to x2, and just to use some other notation I will use say y hat dx, okay, where y hat is nothing but the equation for this particular line. Okay. So now this particular line, the equation for that is going to be essentially y minus y1 divided by x minus x1 equal to y2 minus y1 divided by x2 minus x1. Okay. Or in other words, we take x minus x1 and multiply it throughout, and we just rearrange that. We will be able to write y equal to y1 plus x minus x1 divided by x2 minus x1 multiplied by y2 minus y1. Okay. And because we are representing this as y hat, I will just put the hat signs over here. Okay. So now what the area under that trapezoid is nothing but integral of this particular part dx from x1 to x2. So we will just substitute that over here. So we have integral from x1 to x2 y1 plus x minus x1 times alpha, or rather than using alpha I'll need the term alpha later on, so I'll just call it instead of that something beta. Okay, so y plus x minus x1 beta times dx, where beta I have just called this as y2 minus y1 divided by x2 minus x1. Okay, so when we integrate this, we are going to get y1 minus x1 beta, that is the constant, multiplied by x going from x1 to x2, okay, plus beta multiplied by x square by 2 from x1 to x2. Okay, so y minus x1 times beta is a constant, integral y minus x1 beta dx is y minus x1 beta multiplied by x. The limits of integration are from x1 to x2, and likewise here we have beta multiplied by x, this term when we integrate that it is going to be beta x square divided by 2 going from x1 to x2. Okay, so let us substitute those values in there. So I is going to be approximately equal to y1 minus x1 beta multiplied by x2 minus x1, okay, plus I will have beta by 2 x2 squared minus x1 squared. I will substitute the value of beta over here in a moment. I will just write it down. We have y1 multiplied by x2 minus x1, I will call that as h, okay. X2 minus x1 is this distance h, so I will just substitute that over there. So I will have y1 multiplied by h minus x1 y2 minus y1 divided by x2 minus x1, that was the value beta, multiplied by x2 minus x1, this gets cancelled, plus y2 minus y1 divided by 2 times x2 minus x1 multiplied by, so x2 squared minus x1 squared, I will write that x2 plus x1, x2 minus x1, and the x2 minus x1 will get cancelled. Okay, so we have y1 multiplied by h minus x1 y2 plus x1 y1 plus y2 minus y1 divided by 2 multiplied by x2 plus x1. Okay, so this we will be able to expand this as y2 x2 by 2 minus y1 x2 by 2 plus y2 x1 by 2 minus y1 x1 by 2. Okay, plus x1 y1. Okay, and we have x1 y1 by 2 and x1 y1 over here. So this will get cancelled and we will just divide this particular guy by 2. We have x1 y2 and we have this x1 y2, so this will get cancelled and we will just be able to divide this by 2. Okay, so we will write this as y1 h, okay, minus y1 multiplied by x, so we will plus y1 by 2, we will look at these two terms, and that is x1 minus x2, okay, plus y2, and then we will look at these two terms, and that is going to be y2 divided by 2 multiplied by minus x1 plus x2. Okay. Minus x1 plus x2 is nothing but h, and x1 minus x2 is nothing but minus h. So we have y1h minus y1h by 2 plus y2 by 2 multiplied by h. Okay. And that we will be able to write, this will get cancelled and this becomes y1h by 2, we will be able to write this as h by 2 multiplied by y1 plus y2. Okay. So the integral I using trapezoidal method is written as I using the trapezoidal method is h by 2 multiplied by y1 plus y2. If we go back and look at the geometric derivation, that is exactly what we had obtained as the integral I using the trapezoidal method. Okay. So the trapezoidal method, the sense of it is you take two data points, connect those two data points by a straight line and find the integral under that straight line. The third method we will use is based on Newton's forward difference formula. Okay. And if we recall, the Newton's forward difference formula for two data points was nothing but y1 plus alpha multiplied by delta y1 plus so on and so forth, right. So if we were to write a polynomial y of alpha, okay, then we would be able to write this as y1 plus alpha times delta y1 plus alpha multiplied by alpha minus 1 times delta squared y1 divided by 2 factorial plus alpha minus 1 alpha minus 2 delta cubed y1 divided by 3 factorial plus dot dot dot. Okay. So depending on how many data points that we have, we will be able to write it as a longer series. Now when we have just two data points, we are going to retain only the first two terms. For the Newton's forward difference formula, we had alpha was equal to x minus x1 divided by the h, which is delta x is nothing but h in this particular case. So it was x minus x1 divided by h. So therefore when we differentiate this, we will get d alpha equal to dx by h or dx equal to h times d alpha. Okay. So this is what we will get when we substitute the value of dx in terms of d alpha. Okay. So let us recall what integral I was. Integral I was going from x1 to x2, integral of y hat x dx, that was the approximate value of the integral. Okay. When it comes to the trapezoidal rule, x1 corresponds to alpha equal to 0, you substitute x1 over here, we get alpha equal to 0, you substitute x2, we get alpha equal to 1. So based on the Newton's polynomial, we will have the integral going from 0 to 1. Y hat is y1 plus alpha delta y1 okay. So that is going to be our polynomial multiplied by dx, dx is h times d alpha, okay. And now we do the integration and we will get this as h multiplied by y1 alpha and alpha going from 0 to 1 plus delta y1 multiplied by integral alpha dx, and alpha dx is going to be alpha squared by 2, again going from 0 to 1, okay, and this is going to be nothing but h multiplied by alpha is going from 0 to 1 is going to be 1 minus 0, so it is just going to be y1 plus delta y1 was nothing but y2 minus y1 multiplied by alpha squared by 2, so that is 1 minus 0 divided by 2, so that is going to be 1 by 2, okay. So therefore we have y1 plus y2 by 2 minus y1 by 2, y1 minus y1 by 2 is going to be plus of y1 by 2, so therefore we will have this as equal to h multiplied by y1 plus y2 divided by 2, okay. When we do this derivation, we find that the final value of the integral was the same that we obtained using our geometric or our algebraic methods for joining the two points with a straight line, okay. Now the question is, why did I go through an additional method in order to figure out what the same integral is? The reason I went through this additional method is because the Newton's forward difference formula, using the Newton's forward difference formula, we can figure out what the leading error term is, okay. So when we are just using two data points, if we had an additional third data point, our polynomial would be even more accurate, but we are not using this additional third data point, and that additional point that we are actually throwing away is going to give us an idea of what the error of this particular method is, okay. So the error of this method, and this was something that I did not cover in the previous lecture, using mean value theorem, actually it can be proved that the terms that we are discarding away from this point onwards, the error E is of the order of alpha multiplied by alpha minus 1 divided by 2 factorial f double dash of x, that's what it can be proved. So error in the trapezoidal method is of the order of integral from x1 to x2 or integral from 0 to 1 alpha multiplied by alpha minus 1 divided by 2 f double dash of zeta, okay, and dx will be replaced by h d alpha, okay. And in addition to that, each of these is associated with h for this particular guy and h for this particular guy, so we will have an h square term over here, okay. This is the standard error in Newton's forward difference polynomial, okay. So the error for trapezoidal method is of the order of h cube by 2 multiplied by integral from 0 to 1 alpha square d alpha minus integral from 0 to 1 alpha d alpha, okay, which is equal to h cube by 2 multiplied by alpha cubed by 3 from 0 to 1 minus alpha squared by 2 going from 0 to 1, okay, which is h cube divided by 2 multiplied by 1 by 3 minus 1 by 2, okay. So that is 2 minus that is going to be 2 minus 3 divided by 6, so that is minus 1 by 6. So the error is going to be minus 1 by 12 h cube, and I have been forgetting f double dash zeta throughout, so I will just write that over here, multiplied by f double dash zeta and f double dash zeta. Okay. So that is really the error when computing the integral using the trapezoidal rule. Okay. So this is essentially the overall derivation using the Newton's forward difference formula. So what we started off with was, this is the way we will represent using the Newton's forward difference formula. Because we have essentially only two data points, x1 y1 and x2 y2, we are discarding the rest of the terms in the Newton's forward difference formula. The error associated with discarding this rest of the term essentially is this particular guy. Okay. And then what we said is, we substitute dx equal to h d alpha in that equation. When we substitute dh equal to h d alpha, we get this error term as well as we get this integral term. Now next question is, can we do better than the trapezoidal method? And the answer to that, of course you would expect the answer to that is going to be yes, and we have said that other methods that can possibly be used are the Newton's 1/3 rule and the Simpson's 1/3 rule and Simpson's 3/8 rule, and we are going to discuss Simpson's 1/3 and 3/8. Okay, so let us now go on to the Simpson's 1/3 rule and Simpson's 3/8 rule and do the derivations for them. Okay. Okay. So the idea is as follows. Okay, let us say we have any arbitrary curve and we want to find integral from a to b fx dx, is to look at our another point which is a midpoint for this particular guy. So now we have 3 data points. Okay. So we can fit a second order Newton's polynomial to these 3 data points, and the area under that second order Newton's polynomial, perhaps the second order Newton's polynomial would look like this. Okay. So area under this particular yellow curve between a to b will be the area of the approximate integral that we get. Okay. So if we are going to use these 3 data points, we will call them as x1, x2 and x3. Okay. This will lead us to the 1/3 rule. Okay. And what about the 3/8 rule? In the 3/8 rule, instead of fitting out a second order polynomial, we will fit a third order polynomial. In order to fit a third order polynomial, we need 4 data points. So instead of bifurcating this particular region, we will trifurcate that region, we will break down that region into 3 intervals, and those 3 intervals I will mark them, sorry, I will mark them using this red dotted lines, and I will write them using the red chalk over here. They will become x1, this guy is going to be x2, this guy is x3, and this guy is x4, and this will give us 3/8 rule. Okay. Please keep in mind, please do not get confused, x1, x2 and x3 for the 1/3 rule derivation are different from the 3/8 rule derivation. Okay. So please do not get confused over there. The h for the 3/8 rule is going to be, there are going to be 3 h's, all of them are going to be equal, although this one does not look like it is equal, but believe me, it is supposed to be equal. Okay. So we have the overall area from a to b is going to be equal to 3h in case of the Newton's 3/8 rule, whereas in case of the Newton's 1/3 rule it is going to be 2h. Okay. I am using again the same notations just for notational simplicity. Please do not get confused between them, I just repeat that. So if for Newton's 1/3 rule, our h is going to be equal to b minus a divided by 2. Okay. And for Newton's 3/8 rule, divided by 3. Okay, so that is what we have so far. Now what we will do is we will use the Newton's forward difference formula as we did before and derive the 1/3 rule, and then again we will derive the 3/8 rule. Okay, so most of it remains the same until this point, it remains the same. The change happens this point onwards only. Okay, and we are interested in finding I equal to integral from a to b f of x dx. This is our interest. We do not know our function f of x, but instead of that we know the value at several distinct points inside the integral. In case of the Newton's in case of the Simpson's 1/3 rule, okay, for the 1/3 rule we have integral from x1 to x3 y of alpha dx, and dx we will write it as h d alpha. Okay, and what y of alpha are we going to use? We are going to use y of alpha over here, okay, from this point to this point, and x1 is going to be in terms of alpha, x1 will be 0 and x3 in terms of alpha will be 2. Okay, so we will have 0 to 2 integral y1 plus alpha delta y1 plus alpha multiplied by alpha minus 1 divided by 2 delta square y1. Okay, so I by 1/3 rule is going to be approximately equal to integral from 0 to 2 y1 plus alpha delta y1 plus alpha squared by 2 delta squared y1 minus alpha by 2 delta squared y1 d alpha. Okay, so this is going to be equal to y1 multiplied by alpha, okay, where alpha goes from 0 to 2, okay, plus delta y1 minus delta squared y1 okay, I just forgot h over here, should be h d alpha, okay, delta y1 minus delta squared y1 multiplied by delta y1 minus delta squared y1 by 2 multiplied by alpha, and when we integrate alpha we will get alpha squared divided by 2. So we will have alpha squared by 2 from 0 to 2, and the third term is going to be delta squared y1 by 2 multiplied by integral 0 to 2 alpha squared. So it will be delta squared y1 by 2 integral of alpha squared, and integral of alpha squared is alpha cube by 3 going from 0 to 2. I is, and this whole thing will be multiplied by h. I keep forgetting this h all the time, so I will write that right in the beginning. So we have h multiplied by y1 multiplied by alpha, so y1 multiplied by 2 minus 0 plus delta y1 minus delta squared y1 by 2 multiplied by alpha squared by 2. Alpha squared by 2 is going to be 2 squared minus 0 by 2, okay, that is what it is going to be, plus delta squared y1 by 2 multiplied by alpha cubed by 3. So, this is going to be 2 multiplied by 3, and we will have alpha cubed going from 2 to 0. So, it is 2 cubed minus 0 cubed. Okay. That is the overall expression. Now, delta squared y1 is going to be nothing but delta y2 minus delta y1. So, this is going to be h multiplied by 2 y1 plus delta y2 is going to be y3 minus y2 minus delta y1 is y2 minus y1. So, this is y3 minus 2 y2 plus y1. Okay. So, we will have delta y1 as y2 minus y1 minus delta squared y1 by 2 is going to be minus y3 by 2 plus 2 y2 by 2. So, that is going to be y2 minus y1 divided by 2. Okay. This multiplied by 4 by 2, that is 2, and plus delta squared y1, that is y3 minus 2 y2 plus y1 divided by 6 multiplied by 8. Okay. So, that will be h multiplied by 2 y1 plus we will take 2 inside over here. So, that is going to be 2 y2. So, 2 multiplied by 2 y2. So, these two have gone. We have minus y1 minus y1 by 2, that is minus 3 y1 by 2 multiplied by 2, that is going to be minus 3 y1, and we have minus y3 by 2 multiplied by 2, that is minus y3, okay, plus 4 by 3 multiplied by y3 minus 2 y2 plus y1, okay, and we take 3 outside and we will get this. We will remove this 3, we will multiply all of these by 3, okay, and we should, it is just a matter of simple numerical jugglery. So, what we will have is 6 y1 plus 4 y2 multiplied by 3, that is going to be 12 y2 minus 9 y1. So, that is going to be minus 3 y3 plus 4 y3 minus 8 y2 plus 4 y1. Okay. So, the terms in y1 are 6 y1 minus 9 y1, that is minus 3 y1 plus 4 y1. So, minus 3 y1 plus 4 y1 is going to be equal to y1. So, it is h by 3 multiplied by y1. Now, we have plus 12 y2 minus 8 y2, that is plus 4 y2 plus 4 y2, and we have minus 3 y3 plus 4 y3, that is plus y3. Okay. So, the Simpson's 1/3 rule is going to be h by 3 multiplied by y1 plus 4 y2 plus y3. Okay. So, that is our Simpson's 1/3 rule. That is how that is what we will get when we use the Simpson's 1/3 rule in order to find out the integral. Okay. So, to recap, what we actually did was, we in the Newton's forward difference formula, we retained the first 3 terms and then integrated the equation from 0 to 2, okay. And when we did the integration, we were essentially left with this particular formula, okay. And then we substituted the values of alpha and so on into this particular equation, and this is what we ended up getting. Now if we want to derive another higher order formula, that is going to be the Newton's 3/8 rule. And let me remind you what we have to do in Newton's 3/8 rule is to go from integral from x1 to x4 integral f of x dx, okay. We will use pretty much the same idea, but instead of stopping at the third term, we will include the fourth term as well, okay. And for the 3/8 rule, we will have integral. So keep in mind we had integral from x1 to x3 y alpha h d alpha. In this case we will have integral from x1 to x4 y alpha h d alpha, and integral from x1 to x4 is from alpha equal to 0 to alpha equal to 3, okay. Instead of alpha from 0 to 2, now we have alpha going from 0 to 3, y of alpha h d alpha, okay. And what do we need to do in order to modify this? In order to modify this, we just take the eraser. In order to modify this, instead of going from 0 to 2, we need to go from 0 to 3. We have y1 plus alpha delta y1 plus alpha squared delta squared y1 minus alpha by 2 this guy, and I have additional term over here, and that is going to be plus delta cubed of y1 by 3 factorial, which is 6 multiplied by alpha minus 1 multiplied by alpha minus 2. So that is going to be alpha multiplied by alpha squared minus 3 alpha plus 2. So it is alpha cubed minus 3 alpha squared plus 2 alpha, okay, multiplied by h d alpha, okay. So we will have this additional term over here, and all the limits of integral are going to be not from 0 to 2, but instead they are going to be from 0 to 3, okay. So I, as before, will use all of these terms as before, only thing is that integral is going from 0 to 3 instead of 0 to 2. So we will have y1 alpha going from 0 to 3 plus delta y1 minus delta squared y1 by 2, this multiplied by alpha squared by 2 going from 0 to 3 plus delta y1 squared, sorry, delta squared y1 divided by 2 multiplied by alpha cubed by 3 going from 0 to 3, okay. And then we have this additional term in red, this particular additional term in red, we need to get an integral for that. So we will have plus delta cubed y1 divided by 6 multiplied by alpha to the power 4 by 4 minus 3 alpha squared, integral of that is going to be minus alpha cubed, and plus 2 alpha, the integral of that is going to be alpha squared going from 0 to 3, okay. And delta cubed y1 is going to be equal to delta squared y3 minus delta squared delta squared y2 minus delta squared y1, and if we substitute this particular expression into that, I think we should be getting y4 minus 3y3 plus 3y2 minus y1, okay. So this is what I believe we will get when we substitute delta cubed y1 into this particular expression. So now what we have is just left with a bunch of algebraic manipulations, and once you do the algebraic manipulations, we expect to get I is going to be equal to 3h by 8 multiplied by y1 plus 3y2 plus 3y3 plus y4. Okay. This is what we expect essentially to get using the Newton's 3/8 rule and the Simpson's 3/8 rule, and the name 3/8 basically suggests that we have 3 by 8 as a constant over here. Okay. So just to recap, the Newton's the Simpson's 3/8 rule is this guy, the new Simpson's 1/3 rule is I equal to h by 3 multiplied by y1 plus 4y2 plus y3. The trapezoidal rule I equal to h by 3 I equal to h by 2 multiplied by y1 plus y2. Okay. So this is the Simpson's 3/8 rules, Simpson's 1/3 rule, and the trapezoidal rule. So to recap, what we have done so far is we started off with the trapezoidal rule. We recapped the geometric interpretation of the trapezoidal rule. Then we used Newton's interpolating polynomials, specifically the Newton's forward difference formula, in order to derive the trapezoidal rule, the 1/3 rule, and the 3/8 rule. With respect to the trapezoidal rule, we also saw how to derive the error conditions. I have not derived the error conditions for Newton's 1/3 the Simpson's 1/3 or the 3/8 rule, but those can be derived in the same way as we have done the previous derivation. And finally we have shown how to use the trapezoidal rule, 1/3 rule, and the 3/8 rule. In this particular case, h is going to be equal to b minus a by 3. In 1/3 rule, h is b minus a by 2, and in trapezoidal rule, h is equal to b minus a. Okay. So now what we will quickly do is go to Microsoft Excel and use the trapezoidal rule, 1/3 rule, and the 3/8 rule. Okay, so now let us use Microsoft Excel in order to get the numerical integrals of the equation. This is the equation that we have been using for a fair number of lectures now. F of x equal to 2 minus x plus ln x. If we integrate this, we will get 2x minus x square divided by 2 plus x ln x minus x plus 2x and minus x will result in just one single x over here, and plus there will be a constant of integration c. Okay. So let us say we want to get integral I from a equal to 1 to b equal to, let us say, 2. Okay. And that is what we want to do using, say, the trapezoidal method. Okay. So the trapezoidal method, we want to write out the x. The first value is going to be 1, the second value is going to be h multiplied by 1. So one straightforward thing that we can do is we can split the entire interval into one single interval as we have done with the derivation, and our the next value is going to be equal to just b. So let's write down h over here, and h is going to be just equal to 1. So our next value is going to be previous value plus the value of h. Okay. And then we will put dollar signs over there. Okay. And then let us compute f of x. F of x is going to be nothing but equal to 2 minus x plus ln of x. Okay, that is our f of x. Okay, I will call this trapezoidal rule. Okay, and I will just increase the font size so that it is clearly visible. Okay. Okay, so this is what we have using the trapezoidal rule. F of x is going to be this. So our integral I is going to be nothing but h by 2 multiplied by f of x. So that is going to be equal to h by 2 1, and I will put the dollar signs over there, divided by 2 multiplied by y2 plus y1. So that is y2 plus y1. Okay. Oops. Yeah, y2 plus y1, and I press enter. Okay. So this is going to be our integral I. The true value of integral is going to be equal to x, so that is going to be b minus a, right. So it is 2 minus 4 divided by 2, so that is x minus x square by 2 plus x ln x, that is 2 multiplied by ln of 2, okay, that is the value at b, minus the value of at a is going to be 1 minus 1 square divided by 2 plus 1 multiplied by ln of 1. Okay. So 0.88629 is the integral, and integral using the trapezoidal rule, if we were to use one single one single interval, is going to be as shown over here 0.48657. Okay. So instead of that, what if we choose two intervals? So we will choose our h as equal to 0.5, okay, and then we will just drag this, we will just drag this, and the actual value of integral is going to be equal to sum of these two values, and that is 0.87602. So we have now improved the value of integral by going, instead of just one single interval, by going to two intervals, we have improved that value. What if we go to three intervals? So it is going to be 1 divided by 3 as the value of h, and then we just drag this, we just drag this, and this is going to be sum for this entire batch. Okay. And as we have now increased the number of intervals, the value of the approximate integral has improved. Okay. So when h, using the trapezoidal method, when h was equal to 1, I will write down when h equal to 1 by 2, and when h equal to 1 by 3, using trapezoidal. Okay. Using h equal to 1 by 3, the value I will just paste it over here, paste special values. Okay. When h equal to 1 by 2, the value was 0.87602, I will paste it over here, and when the value of h was 1, that means we had one single interval, this was the value, and I will do the paste special and the values over here. Okay. So, this is the trapezoidal rule. Okay. So, what do we find in trapezoidal rule? As we increase the number of intervals, or as we decrease the delta x or h value, we improve the integral value and come closer and closer to the actual true value of 0.88629. Now, we will use 1/3 rule. Okay. In 1/3 rule, we will have to use h equal to 1 by 2. Okay. So, we will get the value of value of f of x at x equal to 1, x equal to 1.5 and x equal to 2. Okay. And the integral is going to be equal to h by 3. So, that is h divided by 3, and I will put dollar signs, multiplied by f1 plus 4 f2 plus f3. Okay. So, this is the value of the integral obtained using the 1/3 rule. Okay. So, if you compare the value using h equal to 1 by 2 using the trapezoidal method versus using the 1/3 rule, we will see that the value of the integral using the 1/3 rule is closer to the true value than it is for the trapezoidal rule. Okay. And finally, we will use the 3/8 rule. Okay. And for 3/8 h is 1 by 3. Okay. And the integral using the 3/8 rule is going to be equal to 3 multiplied by h, and I will put the dollar signs over here, divided by 8 multiplied by f1 plus 3 multiplied by f2 plus 3 multiplied by f3 plus 1 multiplied by f4. Okay. And that is the value we get for the integral using the 3/8 rule. Okay. And this is what we are going to compare if we intend to. So, I will shade them, and this is to be compared, and so I will shade them with a different color. Okay. So, to summarize, with h what we have done so far is use the trapezoidal rule. We wanted to find integral from 1 to 2 f of x, where f is given this way, f of x dx. The integral 1 to 2 by using just single interval in trapezoidal rule had fair amount of errors. When we go to h equal to 1 by 2 and repeat the trapezoidal rule application twice, the error becomes significantly smaller, and when we apply the trapezoidal rule 3 times, the error decreases. If we decrease h further and further, the error will keep decreasing further. Okay. Then we considered the Simpson's 1/3 rule, and Simpson's single application of Simpson's 1/3 rule allows us to compare the result we get using 2 applications of the trapezoidal rule, and we find that the Simpson's 1/3 rule is more accurate than the trapezoidal rule. And then when we can get 3 applications of trapezoidal rule and compare it with the 3/8 rule, and 1 application of 3/8 rule is more accurate than 3 applications of this of the trapezoidal rule, and 1 application of 3/8 rule is also more accurate than the 1/3 rule. Okay. So, essentially that is what I wanted to cover with respect to the numerical integration using what is known as the Newton-Cotes integration formulae.